Sound. Today we're talking about sound. Sound, first off, is a longitudinal wave. If you remember, longitudinal waves are waves whose compressions, or their crests or their troughs, regardless of how exactly you want to describe it, they're in the same dimension as the way the wave is traveling. So if we look here at some source of sound, okay? Some source of sound right here. Let's do this in green. It is sending out these sound waves, okay? And which way is that wave traveling? Well, the way I've drawn it, it's traveling to the right. So what's the direction of these compressions of the air? Well, it's in that same direction. And then what's the direction of those compressions and expansions? What's the direction of those expansions? They're in the same dimension. So everything's all in the same dimension. That makes this a longitudinal wave. Remember that a transverse wave is the opposite, right? As the wave moves from side to side, as the wave moves one particular direction, your amplitudes are in the perpendicular direction. Okay? But this is a longitudinal wave. All right? The second thing is that sound is a mechanical wave. Okay, it's a mechanical wave. What does that mean? Mechanical waves require a medium to travel through. So what does that mean? That means that the way sound works is it works by pushing on the air molecules one by one. The one in front pushes on the one next to it, and that air molecule gets shoved and pushes the one next to it. And so it's constantly pushing something, all right? Now, if you imagine, what if there were nothing? What if you're in space and you clapped your hands? What would get pushed? Nothing. So mechanical waves have to have something to travel through, whether it's a ripple in a pond, whether it's a sound wave like this, whatever it is, mechanical waves require some sort of medium to travel through. Okay? Let's look at how we actually do some math with sound waves. Okay? Velocity is frequency times wavelength. Okay? V stands for the speed of sound. And it turns out the speed of sound is actually different in different media. So in air, the speed of sound is approximately 340 meters per second. In water, it's a little bit faster. In as you go higher and higher up into the atmosphere, it gets thinner and thinner. The speed of sound actually slows down because it's harder for the air to travel. A sort of general statement is if you increase density, then you increase the speed. Okay? So sound waves travel faster through water than they do in air. Sound waves travel faster in a metal bar than they do in water. So the closer the molecules are packed next to each other, the faster those compressions, those pushings of the molecules are going to actually travel. So the faster the sound will travel. Okay, what does F stand for? F stands for frequency. Now frequency is important because that is actually how we, as humans, interpret pitch. So how high or low a note sounds is pitch. Okay, so it turns out that we as humans can hear from about 20 hertz, that's the lowest frequency we can hear, up to about 20,000 hertz. That's the highest frequency. 20,000. Try that again. 20,000 hertz. Anything less than this is called infrasonic. Anything greater than this is called ultrasonic. Okay. Just to kind of give you a feel for how those numbers go. All right. 20 hertz would be a very low note that you could barely tell was sound. And the 20,000 hertz would be those really, really high-pitched noises that always annoy you. Okay? As you get older, you actually lose some of this higher end, and your frequencies you can hear actually drops lower and lower and lower as your body ages. Okay. The last thing we want to look at is wavelength. Okay. This right here, lambda, remember, is wavelength. For sound, that deals with the distance between these compressions. Okay, is wavelength. For really, really low notes, those are actually really, really large. As low as, in fact, if you do 340 meters per second with 20 hertz, the lowest one is actually 17 meters. 17 meters. That's really, really far. It would not fit inside of our classroom. So they can be really, really large. Versus 20,000, we'd move the decimal place 3 times. They go to about 0.017 meters. So about 2 centimeters. Okay, did I do that right? 1, 2, 3. 1, 2, 3. Yep, about 2 centimeters. This is about the smallest sound wave that we can hear. Okay, so that is sound and how we do that. You could be given a calculation to do, but more likely you'd be asked something about if it's traveling in a different medium, how would that affect the frequency, how would that affect the wavelength. All right. An important thing to remember about sound is that the thing that's always going to stay constant is going to be that wavelength. Okay, the wavelength of sound is what's constant, whereas the frequency changes whether it's in faster or slower. An example of that would be helium. The speed of sound in helium is much higher, which is why let's write out velocity equals frequency times wavelength real quick. The wavelength is going to stay constant. So in helium, the speed of sound goes up, therefore let's do this in a different color. The speed of sound goes up in helium, so the frequency goes up. So that's why we hear it as a higher note. There's actually substances where the speed of sound is actually lower, and there's actually a Mythbusters video about that. Ask me in class and I can show you. The speed of sound is lower, and so your voice would actually sound lower if you talk through one of those. Okay? So that is kind of a quick overview of sound. One particular thing we can look at when dealing with sound is the Doppler effect. No, we're not talking about Sheldon Cooper. What we're talking about is how the wavelengths and the frequency shifts as objects are actually moving toward you or away from you. Okay, so if we imagine that there is some source, let me move this up here. Okay, if we imagine that there is some source of sound, okay, like we had on that first page, it is sending out every time it makes a little bit of noise. It sends out a wave. Okay, and these are concentric circles. All right, but here's the deal. That was really hard to draw. What happens if, as this particle is making these sounds, it actually starts moving? Well, you can imagine that it makes the first little sound, and then it actually moves a little bit to the right. So as this one grows, it's actually getting, its center is back here, and actually your circles end up like this. Okay, and that's why I brought a picture in up here, because I can't draw that well. So here we have, can I draw on that? Can I draw on this layer? Yes, I can. Okay. Here, as this ambulance is actually moving towards this person, it sends out a little bit of sound, but then it moves toward that sound it just sent out, and so those sound waves are actually getting compressed up here in the front. They're getting closer together. If they're closer together, then they're reaching the person's ears more rapidly than they would normally reach the person's ears. So they're going to interpret that as a higher frequency. Okay? So here, the frequency seems higher to this person because you can tell that they're actually getting all compressed together. you could actually tell that the wavelength is getting shorter. Okay, so the frequency is going up, you hear a higher note. Okay, what happens when the ambulance passes you and it's going away from you? Well, now it sends out a little bit of sound and moves away from it. Sends out a little bit of sound, moves away from it. So these wavelengths are actually being stretched out here. So you're actually hearing them less frequently than you normally would. So you actually hear a lower pitch. So here the frequency would be lower. So these are the two key things when dealing with the Doppler effect. If the object, Doppler effect. If the object and the observer are moving, the object that's creating the sound and the observer, the person who's hearing the sound, are moving toward each other, then we know that the frequency is going to be higher. And if they're moving away from each other, then the frequency is going to be lower. Well, the question of how much lower deals with how quickly is the object that's creating the sound, or the observer, how quickly are they moving toward each other? So in both cases, the faster the velocity, the more dramatic the effect. So let's write higher velocity means bigger shift. Okay, so a few examples of this. If I'm walking around the classroom while I am teaching, are you going to hear an audible difference in the pitch of my voice as I'm moving towards you, as I'm moving away from you? No, you're really not, because I'm really not moving very quickly, so the shift in frequency is very, very small. But let's think about like a race car as it drives past you. What noise does a race car make as it drives past you? Think about it. I'll embarrass myself and make the noise. It goes, eeeew. All right, so what did it just do? If you notice, it started out at a high pitch because it's moving toward you. Let me move so I can write on this one. It's moving towards you, so it's making a high pitch. As it moves away from you, it makes that lower pitch. So you hear the eeeew, right? Higher as it moves towards you, lower as it moves away from you. Okay. Another example is if someone falls off of a cliff, you're standing at the top listening to them fall off the cliff. Well, what's happening to their velocity as they fall? Well, they're accelerating towards the bottom of this cliff. They're speeding up. They're going faster and faster and faster. And as they fall, are they moving toward you or away from you? Well, they're moving away from you. So the frequency is going to be lower, and the faster they fall, the bigger the shift. So what do you hear when a person falls off a cliff and screams? Well, you hear, ah, right? It gets lower and lower. Do you think the person who's screaming is actually changing the pitch of their voice while they're screaming? Of course not. They're just screaming. They're screaming a nice constant note. Okay? But why does it sound lower and lower and lower as they fall away? Is it because necessarily they're getting farther away from you? Is it based on distance? No, it's only based on velocity. As they fall, they're accelerating, going faster and faster. So this shift to a lower frequency is getting more and more dramatic as they fall. Okay? Doppler effect is used in tons of applications, from shooting waves towards clouds to see how the weather's moving around, to looking at the light coming from stars to tell how fast the star is moving towards the Earth or away from the Earth. Lots of different things like that. It also contributes to why ice cream trucks always sound slightly out of tune, because as they drive towards you, the pitch is a little too high. They drive away from you, pitch is a little too low, so they always sound a little bit out of tune. All right, let's talk about our last topic, which is beats. All right, so here I've drawn a wave. Let's look and see what the frequency of this wave is. Well, it actually goes through one. Let me draw on this one. Goes through one, from here to here is one wavelength. From there to there is 2 wavelengths, and one more that is 3 wavelengths. So it traveled 3 wavelengths in a certain amount of time. Let's say it traveled those 3 cycles in 1 second. Let's say this whole thing took 1 second. Then the frequency would be 3 hertz. Okay? 3 cycles per second. 3 hertz is the frequency. Okay? Let's draw a different wave. Let's draw it in pink. Let's draw one that is half as slow. Okay? So what's happening to this wave? How are these 2 waves going to interact if you played them both at the same time? Well, notice at the very beginning, right here, actually before we do that, how many hertz is this wave? Well, it actually goes through 1 full cycle to here, and then it goes through half a cycle. So it actually has a frequency of 1.5 hertz, 1.5 cycles in this time period. Okay? Now, let's look at interference. If you played both of these waves at the same time, both of these frequencies at the same time, what are you going to observe? Well, right here you get constructive interference. Put a C for that. But what happens here? Here you have a crest lined up with a trough. What kind of interference are you going to get there? You're going to get destructive interference right here. All right? You get some more destructive interference right here. More destructive. Whoa, check this out. Now they're both troughs. So you're going to get constructive interference again. And you got both crests right here. You get constructive. Oh, but now they're opposite again, right? Crest with a trough. You get destructive. So notice it's switching back and forth between constructive, destructive, constructive, destructive. So it's switching back and forth between adding to the amplitude to then subtracting from the amplitude. So it gets louder and softer and louder and softer and back and forth and back and forth. Okay? And how frequently that louder, softer, louder, softer, louder, softer thing happens depends on the difference between these 2 notes. Okay? So in our example, the difference between them happens to be 1.5 because it was going half as slow. But let's do a different example. Let's say I'm playing the guitar and one note that I play is 440 hertz. That happens to be the note A on a guitar. Let's say that someone else is playing another note on a guitar that's very, very similar, but they're playing 442 hertz. So it's slightly too high. So you're going to hear this as a slightly higher pitch. So what are we going to observe if we play both these notes at the same time? Well, they're going to start out lined up. One will be a crest, the other will be a crest, lined up. But by the time you get to the end of 1 second, one is going to be back at a crest and the other is going to be back at a trough. So you're going to get destructive interference. And that's going to happen how many times every second? How many times is it going to flip back and forth? Well, what is the difference between these 2? We would literally subtract them. So the frequency of the beats that we hear, the frequency is 2 hertz. And the beats we're hearing is a louder sound followed by a softer sound. A louder sound, softer sound. Louder sound, softer sound. Turns out if we played these 2 notes right next to each other, we would hear 2 beats per second. All right? So that is sound in a nutshell.